All right, welcome back, everyone. Happy Wednesday. We are in the middle of Unit 2, which is analyzing systems for their transient response. So last time, we talked about what is the transient response. We talked about how does the transient response change as your complex conjugate poles move around the plane. We talked about that you can represent the locations of those poles either in our Cartesian or rectangular coordinate system, or in this kind of new quote-unquote polar coordinate system that makes use of the quantities called the natural frequency and the damping ratio. And if you rewrite the pole locations with those coordinates, then the transfer function can always be written in this form, provided you started with a underdamped, stable, second-order system with no zeros. So if that is all true, then your transfer function can be written in what's called canonical form. And that means that just from looking at the denominator polynomial, you are free to recognize the natural frequency and then the damping ratio after a little bit of algebra. So today I want to carry on with taking the impulse response in the new coordinate system and soldiering on to write the step response. Okay, so here begins the new content of today's lecture. So as you know, the output to any LTI system can be written as the input convolved with the impulse response. So what I've just done here is I've taken the impulse response from the last slide and I've convolved it with a unit step. That unit step serves to clip the limits of integration from 0 to t, and the integral will be over a dummy variable tau. Now I'm skipping a lot of details here because we all suffered through 228 and I don't want to subject you to that again. But the idea is that you could, what would you have to do here? You'd have to do re-emergent integration by parts. So this is integration by parts to get a cosine, integration by parts to get a sine, and then factor it all out to get the next line, which is what I did and what you don't have to do. And then what I do to the third line, I simplified a bunch of terms and collected them. And this is what today's lecture is mostly going to be about, this equation. This is the step response. Of a canonical underdamped system. Okay. So all the players are present. The K is present. The damped natural frequency is present. The angle that the poles form with the negative real axis is present. We call that beta. The cosine of that angle, we call that zeta, is present. And the hypotenuse, the distance of the poles to the origin, is present. We call that the natural frequency. All of those four things come into play in this equation. So that's fine. I think this is a pretty tricky thing to visualize, which is why I plotted it for you here. So again, this is horizontal axis time, vertical axis, the output of the system. And if the system is underdamped, it should come as no surprise that we have this oscillating type response. So let me copy that equation so we have it for reference here. So this is the plot of K times 1 minus e to the minus zeta omega n t all over square root of 1 minus zeta squared times the sine of the damped natural frequency times t plus beta. Okay. So, well, I mean, let's just make sure this makes sense. When t is 0, the exponential becomes 1. The sine omega dt plus beta becomes sine of beta. So g of 0 is k times what? 1 minus 1 over root 1 minus zeta squared sine beta. But if you do a bit of trig, then if this is beta, then sine beta is what? SOHCAHTOA, opposite over hypotenuse? Yeah. So this is omega d, omega n. So sine beta is opposite over hypotenuse. And omega d over omega n is exactly square root of 1 minus eta squared. So everything over here goes to 1. And so g of 0 is 0. Okay, just to show you I'm not making this up. As t goes to infinity, what's g in steady state? Well, the exponential will go to 0. So I think g in steady state is just k. All right. So I've got some animations lined up here. There we go. Some relevant quantities that you might want to pick off of this graph are, of course, the steady state value, which we just solved for. The maximum value, that's an interesting quantity, right? If you're trying to design a system, it's reasonable to expect that the maximum value of your output is a design quantity, like you don't want it to be too big or too small. So those are all very relevant quantities.
It's 1 minus 1. How is g of 0 equal to k instead of 0?
But 1 minus 1 is 0. So 0 times k is 0.
So why is g of s equal to k instead of 0?
So g steady state is my notation for g as time goes to infinity. Two separate things. Okay, so what I'm going to introduce on this slide, what I wanted to introduce on the slide, is this notion of transient metrics. And a metric is a measurement. It's a measurement on something. So what we're going to be doing is we're going to be measuring the transient response. We're going to be quantifying the transient response in a way that's not a graph. We're going to attach some numbers to it so that we can say, oh, this response is better than this response. How do I know that? Well, the numbers are better. Okay, that will make a bit more sense in a second. But the first transient metric I want to introduce is this notion of overshoot. I abbreviate it OS. I think your book abbreviates it M sub P. But anyway, it's the idea of this distance relative to this distance. How high is your peak relative to your steady state value? Clearly, when that number is smaller, this peak is smaller. When that number gets bigger, then the peak gets larger. You'll often see this written as a percentage. So percent overshoot would just be G max minus G steady state over G steady state times 100%. Okay. So don't let the percentage versus decimal fool you. Another metric, let me see if I can erase this. I can, sweet. Another metric that is relevant is called the peak time. It's pretty self-explanatory. It's the time when the response peaks. The idea here is that a fast system, will have a small peak time, and then it will get on with its business. Something else you might want to measure is called the rise time. And again, this is the time it takes the system to first rise to its steady state value. Again, faster systems have smaller rise times. I want to give you a heads up. Those of you who are taking 307 this quarter, I believe that you will have a different definition of rise time. So just a heads up, there are different definitions out there. There's what's called the 10 to 90 rise time. And that's different than what I'm defining. This is, in some senses, the 0 to 100% rise time. Whereas in, I think, 307, they want you to use the 10 to 90% rise time, which would just be the time between these red lines. We're not going to use that quantity here in this class. Okay, so you got peak time, you got rise time. I think probably the most important of all these metrics is how quickly do the oscillations die? Like, usually the oscillations are bad. So if you could give me a measure of how quickly the oscillations go away, that would be super useful. Bad news, the oscillations never go away, right? They are always ringing and ringing and ringing. Their amplitude gets smaller, but we're going to have to introduce some kind of tolerance. And so that's this notion of the plus or minus delta percent settling time. So let me work you through this for a moment. If you ask, when does the system completely settle? The answer is never. If you ask, when does the response decay to within plus or minus 2% of its steady state value, that has a finite answer. So what you just asked me was, what is the 2% settling time? And in terms of the notation on this graph, it's the delta equals to 0.02. Okay? So different jobs will have different settling time requirements. You can think about, so for example, you could think about the 2% settling time. That's a common one. You could also think about the 5% settling time. And if you really didn't care, you could talk about the 10% settling time. All of these are valid metrics, but they're all different. They're different in that if I change the delta here, I will change the height of this tunnel. This tunnel is plus or minus delta percent around the steady state value. So as soon as we fix the delta, then we can draw this tunnel, these horizontal bars. And now comes the fun part. Now we get to move our pencil along the curve and find the first time the system stops leaving the tunnel. Said another way, it's the last time the response is ever outside the tunnel. Okay, so let me, I've got it annotated here. For this particular delta, this is the delta percent settling time. And again, it measures the time it takes the system to guarantee that it's no more than delta percent away from a steady state value. Questions on that?
So basically, that parameter is where it's the last bump is going on, exactly, kind of.
Well, I mean, there are infinite bumps,
Mm-hmm.
but you can think of it as the last time the bumps are bigger than delta, if you like.
Okay, I see. All right.
And it depends on what we set for our delta values for the upper and lower part of this tunnel. That again, the time is outside it is when we actually care from there and onward.
Right. So here you can test your understanding of this. If I drew on this slide the delta equals 2%, what would happen to the settling time if I recalculated the 5% settling time? Would the settling time get shorter or longer?
Shorter.
It would have to get shorter because the bars would get higher. And now all of a sudden, here is my, say, T 5%, for example. Okay? But good. What delta is a tolerance. And if your tolerance gets looser, then your performance gets better. Said the other way, if your tolerance gets tighter, then the metric will get larger, will get worse.
This may be a silly question, but what exactly is it 2% of? Is it like 2% of the, that value? Like if the GSS were to be a smaller number, would the 2% have a larger impact?
No, it's the percentage of the steady state value. So think about this parenthetical. That would be 1.02 times GSS. So this is 2% of GSS up, and this is 0.98. So this is 2% of GSS down.
Oh, I never mind. I see.
Yeah.
And so can we think of tolerance, I guess, in a way kind of like efficiency? So like if our system is like more efficient, then it can have like it can support like a greater tolerance?
That's a bit context dependent. I think of the settling time threshold as you look at the system that you're trying to design for, and you ask yourself, when can I consider this system to have settled? And that answer will be different if you're trying to, I don't know, point a satellite at a point on Earth, where you have to have very small oscillations for it to be accurately pointed, versus if your oven fluctuates by 10% or 5%, that's probably not a big deal. So if I was designing an oven control system, then my settling time might be defined by the 5% settling time. But that's because of the context of the system that I'm talking about, not necessarily the efficiency of the system per se. So here is that canonical step response formula, and I want to present to you how one would find formulas for those 4 metrics that I just presented. So the easiest one is to find the peak time. So I'm skipping over a whole bunch of derivation here, but the idea is you could differentiate g with respect to time. You could set that derivative equal to 0, and you could solve for the times for which the g function has a peak or a valley, and then you would pick the very first of those times. If you did that entire procedure, you would get this formula. So what I'm trying to say is that the peak time of a canonical underdamped second order system is governed exclusively by the damped natural frequency. Pi is just pi 3.14. Likewise, you could go through a similar procedure. You wouldn't have to differentiate, but you would say take g of t, set that equal to k, and solve for the first t that makes that true. That would give you the rise time. And if you did that procedure, you would get an expression that looks like pi minus beta over omega d. So check the units on this. These are, in the numerator of both of these are a radian quantity, and the denominator is a radian per second quantity. So we end up with units of seconds. To find the settling time is actually a pretty involved calculation. What this formula presents is pretend the system didn't oscillate, pretend that we are just looking at these plus or minus exponential envelopes. Then this formula gives us the answer, when do those envelopes cross the delta threshold? Okay, so that's why I have this approximately equals to sign here, is because this formula solves for when the envelope crosses the delta threshold, not the response. And sometimes those can be different because the response clearly doesn't live on the envelopes, it bounces between them. Okay? But the important bit here is that as delta gets bigger, then the log of delta, what happens? That also gets, how does that work? Delta gets bigger, then the log of delta gets bigger. But we're taking the negative. Okay, so that'll get smaller. Gotcha. So again, like we said, as the threshold increases, the settling time should decrease. The other relevant metric here is that the only parts of the system that play into this are the product zeta times omega n. Right, so this is kind of exogenous, but these are endogenous to the system. That is, delta is set by something external, but zeta omega n are properties, are internal properties of the system. Okay? So yeah, there's a lot of Greek on this page, but not all Greek symbols were created equal here. And finally, to calculate the overshoot as a decimal, you would do that same differentiation, or once you had the peak time, you could solve for what is G max, you could solve for G steady state, and then you could derive this fraction. And you would get the overshoot is the exponential of minus pi zeta divided by square root of 1 minus zeta squared. So it's not clear to me, or it wasn't clear to me when I first saw this formula, how the overshoot changes with zeta. But we know that zeta lives between 0 and 1, so I can restrict my graph to look something like this. And so I guess there's no good way of deriving this other than to say that when zeta gets small, should overshoot get big or small? What do you think?
Bigger. Overshoot should get bigger if the dampening's less, right?
That's exactly right. So as zeta gets small, we are increasing the beta angle. And so we're thinking about poles way up here, which are very underdamped. And one way to talk about very underdampedness is large overshoot. Okay, so this curve looks something like that. That is, the bigger zeta gets, the smaller the overshoot gets. The smaller zeta gets, the bigger the overshoot gets. And this is a roughly exponential type curve. So this is going to be one of the biggest, most important diagrams that we do all quarter. So I want to prepare you mentally for that. So I want to copy some of those formulas that we had before. So we had overshoot was e to the minus pi zeta over square root 1 minus zeta squared. And we had peak time is pi over omega d. And we had rise time pi minus beta over omega d. And we had settling time was the natural log of delta over zeta omega n. Okay, so that's, sorry, just copying last slide to this slide. And what I want to do now is I want to place a couple of conjugate poles on the plane. So my question, if we were standing at this pole, in what direction should we walk to get to a new system that has the same overshoot as this system?
Would it be diagonally?
Diagonal with what angle?
With beta?
Precisely.
The direction.
Yeah, the overshoot formula depends only on zeta. And if I want a fixed zeta, I need to walk along that line. Yeah, because that, if I walk along that line, then I have fixed beta, and beta is 1-to-1 with zeta, and zeta is 1-to-1 with overshoot. That's the logic train going on here. So this is a line of constant overshoot. So follow-up question, and then obviously the conjugate down here. The follow-up question is, if I move inside of this cone, does the overshoot get bigger or smaller? So if I go inside, then that means that the new beta angle will be smaller. That means that the new zeta will be larger. And according to the little diagram I just had, overshoot should get smaller. So this is less overshoot. And this is more overshoot. So this is a tough one because you've got to map from beta to zeta to overshoot, and that's tough, having just learned all of these things.
Also, what kind of makes it a little bit difficult is that it's a nonlinear scale.
For sure, but at least we can talk about bigger or smaller without quantifying. Okay, so let's go back to standing on the original system, so standing on one of these x's. If I wanted to walk and get to a system with the same peak time, where should I walk?
Same peak time, WD.
You have to maintain WD, so what does that mean geometrically?
Doesn't WD exist? WD is the magnitude between beta and
Check your slides or check your lecture notes from Monday, I guess.
That's a different W.
Would it be left and right? Keeping
Left,
your-
right. Good job, Brian. So omega D represents the imaginary part of the poles. So this is a line of constant peak time. It's a line of constant peak time because it's a line of constant omega D. And if I can make omega D constant, pi is already constant, then this entire horizontal line will be a line of constant omega D, or sorry, constant peak time. So, follow-up question. If I were to move outwards, if I were to walk from the upper X, if I was to walk north, would I get to a system with a smaller peak time or a bigger peak time?
Is it bigger?
Smaller?
So if I walk north, then I'm increasing omega D, which ought to decrease the peak time, right? Because it exists in the denominator. So this is going to be smaller T peak. Another way to say smaller T peak is faster. We've got overshoot done. We've got peak time done. Oh, I guess I wanted to say that if you move inside here, this is a larger peak time. How about settling time? Let's talk about settling time. So again, we're going to recreate this exercise. We're going to go stand on the X, and we want to move in a direction that has constant delta % settling time. This is equivalent to maintaining a constant zeta times omega n. So what does that correspond to geometrically?
Are you moving along the constant OS line?
That would maintain a constant zeta, but I think moving along this ray would necessarily change your omega n. So keeping zeta constant but changing omega n would then change the product zeta times omega n.
Would it happen to be left or right?
So left or right would change both. Then
Okay.
it would maintain omega d, but actually it's exactly wrong. You want to move up and down. If you recall, zeta times omega n turned out to be negative of the real part of the pole. So if I want to maintain a constant zeta omega n, I need to maintain a constant real part, which means I have to move north and south, up and down. So this is a line of constant settling time. And if I make this denominator bigger, then this is a smaller settling time, and this is a larger settling time. And that has to do with moving along the S-plane doesn't change delta. Delta is exogenous to us. Moving along the S-plane directly left or directly right will increase or decrease, respectively, the product zeta times omega n. So the last one is the rise time. And the rise time is actually the one with the hardest, the least clear geometric interpretation. In fact, because you've got beta and omega d, which has omega n, and zeta, everything changes everywhere you go. But if you zoom in, and this is the only one with a bit of nuance here, if you zoom in, if you travel roughly with constant radius, then you will maintain roughly constant rise time. So this is roughly constant rise time. And that only holds within a small neighborhood of your pole location. So same here. But the same pattern emerges, that if we move inside, this will be a larger rise time. And if we move outside, this will be a smaller rise time. We've got 4 metrics. 3 of them are time metrics. 1 of them is an overshoot metric. All 4 of them have geometric interpretations in the plane. Those geometric interpretations come from the formulas that came from the canonical step response. So that logic train goes, write the step response in terms of zeta and omega n, derive the metrics in terms of zeta and omega n, use the geometric interpretation of zeta and omega n to create the figure we have on the screen now. And the biggest takeaway that I would like you to have from this is that all of the time metrics, that is peak time, rise time, settling time, they all get larger as we move this way. They all get smaller as we move away from the origin. Okay, so this is the major takeaway. If you don't remember anything else in this lecture, it's that poles that are further from the origin are faster. That's the takeaway from today. There's a lot more in the lecture today, but if you can remember nothing else, remember poles that are more distant from the origin correspond with faster time metrics. Questions on that?
I had a question about the rise time.
Okay.
What appears to be like semicircular radius that they have is due to the relation between beta and omega d, correct?
Yeah. If you keep omega n constant and just vary beta slightly, this quantity, let me get the pen up here. So if you maintain constant omega n and vary beta slightly, this quantity remains roughly constant.
Did you mean to say omega d? Because that's what it
No,
says.
I mean keep the constant radius.
Oh, okay, I see.
And then vary the angle. Then this quantity is insensitive to small changes in beta. Yeah.
Professor, this is only for an underdamped, correct?
Yeah, so if the system is overdamped, there's no notion of zeta, there's no notion of omega n, so none of these quantities really make sense. Now, that said, if we change the picture and have an overdamped system, does my sweeping generalization still hold? Are poles further from the origin faster? Can you answer that?
The settling time, would that still hold? That it would be a smaller settling time for the left one?
Exactly, yeah. So if this is, say, at -10 and this is at -1, then this corresponds to a mode that looks like e to the -10t, and this corresponds to a mode that looks like e to the -t. Guess what? This thing does everything it does faster than this thing, right? Because it's the speed of an exponential decay is entirely determined by its time constant, and a time constant is uniquely determined by the pole location if the pole is real. Good, so this is still fast, and this is still slow, relatively speaking, right?
What would this mean for like a simple RC circuit? What would be?
So an RC circuit, if I'm thinking of what you're thinking of, it's just a single resistor, single capacitor.
Yeah.
That's going to be first order, so we can't have complex conjugate poles, right?
Oh, okay. Well, yeah, okay. Thank you.
Yep. So, hey, here we go, an honest to goodness example problem. Let's maximize, okay, sweet. So we're told that the open loop pole location is at -1, and the question is solve for k to ensure that overshoot is small enough. So this is a great first problem, because if you hadn't been in class for the past week and a half, I think this would be really hard. But since you have been in class for the last week and a half, you know that a feedback loop can be reduced to be forward path over 1 plus forward path times feedback path. And if there's no box down here, then you are free to consider that as just a unity gain. Okay? And then I see that the negative sign here corresponds with a positive sign there. And so I can simplify the end-to-end transfer function here as k over s squared plus s plus 1. Sorry, plus k. And this is a second order system. So if I go and I block out everything here, this transfer function describes that system. Now, we can use our canonical form to say that omega n squared is going to be k, because it's the units term down here, which means that omega n is the square root of k. And omega n is a distance, so we take the positive root. And then there's a 1 hanging out here in front of the s, so that we know that 2 zeta omega n has to be 1, right? This is the coefficient hanging out with the s to the 1 term, and this is the coefficient hanging out with the s to the 1 term, so they have to be the same. So that means I can solve that for zeta and get 1 over 2 root k. So that's taking the block diagram and extracting as much information as we can. The next part of the question is, or the next part of the answer would be to recognize that overshoot and zeta are 1-to-1. So if I have overshoot equals 5%, that corresponds with exactly 1 zeta because of this curve that I drew before. This is the overshoot versus zeta curve. This says if overshoot is 5%, zeta is a fixed value. Now I've done that calculation beforehand, and this is zeta of about 0.69. So this is approximately. But you can take that overshoot equation that I gave you, and you can back out the formula for zeta from it. So if overshoot is 5%, then zeta is about 0.69, and I have this formula for zeta. So let's take a moment and think about inequalities for a bit. I have on one side the expression for zeta. On the other side, I have an expression for a limiting value of zeta. And so I need to decide whether this is a less than alligator, a greater than alligator, or an equals alligator, a non-alligator. Okay. So to answer that question, I want to look at this figure again. If I need overshoot less than 5%, that means I need to live below this horizontal line, which means I need to live to the right of this critical value of zeta, which means that the zeta that I have has to be bigger than the zeta that I want. Does that make sense? If you like, there could be a weak inequality here, but I need zeta to be at least 0.69, because that guarantees that I live over here. If zeta were less than 0.69, then I would live up here in the frowny face zone. Okay, so from here we can reciprocate, and we get 2 root k is then less than or equal to 1 over 0.69. Let me refer to my notes, because I actually did this problem. That's 1.449, and square both sides, divide by 2, you get k less than or equal to 0.525. Okay. So let me summarize before class ends. This problem was essentially cumulative. I know it's weird to think about a cumulative problem in the second week, but it relied on you being able to reduce a block diagram to a single transfer function. And then it relied on you being able to identify the characteristic polynomial in that transfer function with our two critical quantities, omega n and zeta. And then it had you identify the zeta, the minimum possible zeta to give a maximum value for overshoot. And so the last bit was to mind this inequality. And if you had flipped that inequality around, you would get the exact wrong answer.
If you have the transfer function, how do you get back to the block diagram?
I don't understand the question. So the transfer function that I have here at the bottom is a simplification of the feedback loop. So this is the R signal, this is the Y signal. And
So is there no way to get a feedback loop from a simplified transfer function?
You can go back the other way. I don't know why you would want to do that, but I think you could do that.
I was just trying to, I guess I'm thinking about question 6 on the homework the wrong way. I was trying to figure out how to get a block diagram from a transfer function.
So I will warn you that a single transfer function can be represented by multiple block diagrams.
Oh.
Yeah. So the condensation from complicated to simple is one directional, usually.
Okay.
Okay, thanks everyone. I will see you in office hours and we'll continue this unit on Friday.